Afternoon, everyone. Just here to introduce Jason Rockson. He's here to talk to you about forced air guidelines. Jason's been working in the heating, ventilation, air conditioning, and refrigeration industry since 1993. He completed his apprenticeship at training in Vancouver, British Columbia, where he was exposed to virtually all facets of the industry, from heavy industrial and manufacturing to light commercial and residential. He has a wide base of knowledge and ability to apply it. So, without further ado, here's Jason to talk to you guys, and hope you have a good show.
Thank you. So we'll go, because I didn't know I was getting introduced, so there's that there. So I am a ticketed refrigeration and gas. I own Mercury Refrigeration. I work on the island. I don't recognize any inspectors, but that doesn't mean they don't work on the islands. But I've been a volunteer for TechF for over 15 years, and I've been teaching this class, which is the heat loss class, which you just had Chris for, the duct design class, which is what I'll be going over, and I teach the ventilation guidelines class, which I don't know if you guys did that this morning, or you guys are doing it tomorrow, whoever's going to take the class. I'm on the vent committee, so I'm the one that tries to recommend to building code officials, like to get the things the way we want them to be in BC, which you guys know is different than the rest of the province, or the rest of the country. I've taken every single class that TECA offers and has certification in all of them, and I'm also certified geothermal. So we'll just start in it at the beginning, just go over some quick stuff that I shouldn't really have to explain a whole lot, and then we'll get more in the nitty-gritty as it goes through a little bit. I have an hour and a half to kind of try to come together on a 2-day class. So I'm trying to pick what I thought was pertinent to you guys and just go from there. If you guys have any questions, just stick your hand up and I'll answer them as we go. We have time, so don't worry about the timeline too much. So heat transfer methods. To get into a forced air system, we can use gas, propane, or oil, like a heat exchanger. So have a flame inside, blow air across it. Nice and simple, lots of those. Refrigeration coil, which would be a heat pump. We can get heating or cooling out of it with other things that we'll go over later. And then the other one is, which has been happening a little bit more lately, in where I am anyways, is using hydronic coils with a forced air furnace and putting in combination systems, which is what you'll get out of Scott after me, which is the hydronic side for in-floor heating and everything else like that. So we're getting a little bit more of combination systems as opposed to people just slamming a gas furnace and an air conditioner in their house. So. Options for distribution: easy, sheet metal, most common. Nothing sizing we'll go over later, but nothing really that complicated about it. Put the biggest to the smallest you can, required by the CFM you have to push. You can run flex duct, which you guys I'm sure have seen in a lot of attics and everything else. So there's a picture for those that haven't seen it, which would be shocking to me. The other one is small flex duct, which has been coming up a little bit more because people are building houses without attics because of ceiling restrictions and bylaws and stuff like that, so they got to bury a lot smaller duct. So they're using what's called high velocity duct or smaller flexible ducts, which would be those, and then running the heating in one of those other three options. Either you run usually a hydronic coil or a refrigeration coil to get the heat into those systems. They're not usually a heat exchanger system because they require a certain amount of air to go across them. So there's the three. Then the other one is that's been coming a little bit more prominent, especially like these houses that don't have a lot of space for ductwork, is they're putting ductless in. So they're putting ductless heads like that in, which would be refrigeration based. And then, or they can put in one like that. They could be refrigeration based, but that's a hydronic coil. So they can run water lines through the house and heat rooms individually with water, as well as a forced air system, which is why the combination systems are coming in a lot more. The big problem you guys have with this, which some of you would know, is the other three, we can get fresh air into the house using the ductwork system that's heating or cooling the house. The problem when we go to ductless is we don't have a way to get fresh air in the house, so then they're still going to have to do something for that. So sometimes there's some added costs that shift things people one way or the other, because we still have to follow all the code for ventilation to bedrooms and floors without bedrooms. So I'll go through heat pumps now for those of you guys that are, because I've seen some people from far away and some people from closer, so some of you may have seen heat pumps and some of you may not. Common one, just air-to-air heat pump connected to a furnace or some kind of air handling device of some kind to blow air around the house, or ductless. So pictures there. So either a side discharge or a top discharge unit. There's no difference in efficiency just by looking at the box. It's just look at the capacity and the specifications. Usually physically, if it's bigger, one of two things is happening. You have more capacity or you have more efficiency, or maybe both. So
does it take, why is there two there? Just because the house needs two?
That was two separate zones. One went up and then you can't see it, but one goes in the crawl space and goes across to the other side of the house. That was just, they used the other side of the house. It was a retrofit application, that house. That was just I was going through my pictures trying to find a clear, bigger picture. So that one's just, they wanted two zones. That was all it was. They're not that big. That unit there and the other picture is a bigger, probably capacity is probably both of those together. So. Next one is air to water. So we can use this by hydronic systems. We can use the hydronic coil for forced air, but most likely if somebody's spending the money on this type of unit, they're putting a radiant floor system in of some kind, or already have one installed and they're putting it in. So there's that there. So that would be what they call a package unit. So everything's inside that box. There's a heat exchanger in there, the compressor's in there, the condenser's in there, everything's in there. This specific one can heat and can cool the water down, and then you're piping that water to the inside. Those systems require glycol antifreeze of some kind in them to make sure they don't freeze out because the unit's sitting outside. So that's the one thing people have to pay attention to that sometimes they don't. They do make a different model, which I had a picture, but it wasn't coming up clear, where you can get a split unit where you run refrigeration lines in between the indoor and the outdoor. That requires no antifreeze because all the water is now inside the heated envelope of the house. So you don't have to worry about it. It just has a condensing unit outside with refrigerant lines. Next one is a water to air. So that would be just the easy math, easy explanation, but that would be a geothermal system, so of some kind. In this case, a water to air. So there's a picture of one. So that's a forced air unit because we're getting the heat from the water and we're putting it into the air. And then in this case, there's a ground loop buried in the ground, either horizontal or vertical. I'll go through that in a sec. The next one is water to water, so we're using the ground or some circulated water of some kind to get heat out of, to produce heated water, which could be used for hydronics or forced air systems using a hydronic coil, or ductless units with hydronic coils in them for heating and for cooling, both. So there's your options as far as geo goes, the basic options. So vertical, drill holes, horizontal loop, and depending on where you live will be the required amount of piping. Open loop would be using groundwater and then pushing it back into the aquifer again, like pushing it through, just taking heat out of it. And then the pond loop would be basically any water loop, so ocean, lake, or pond. Yeah?
Heat pumps, I believe, at least a few years ago, there's a limit to the cold temperature they can work out efficiently. It's not a factor on the island, but farther north is zone 7A. Colder winters, they were really considered to be effective. It's going to be -8. Has that temperature changed now?
No, it's changed quite a bit. I go over it in a little bit, but I'll answer the question anyways. So what we have to be careful of is when you size a heat pump, like if we go back, here, let's go back to the picture of the two heat pumps, because those two low ones are actually high. That little red square you can't really read, it's a low temperature heat pump. So what it means is that heat pump will provide full capacity down to -15 Celsius. So, and will run down to -30. Whereas the one up in the top corner will be losing capacity basically from 10 degrees Celsius down. It'll continue to lose capacity and lose efficiency and everything as it gets colder. And it will get to a point that it'll still be probably more efficient if your choice is electric, but if you have other choices, then it would be better to use the other choices. Because
I'm just recommended sub-units, a backup heat source is recommended.
Yeah, I'll go over when it's recommended in a little bit. That's all good, but I'll go over it and I'll explain it a little bit better with the pictures and stuff like that. But that's a good question. So, is there anything else?
What, maybe you're gonna go over it later, I don't know, but you said that one heat pump could go down to -15 and still be efficient.
Yeah.
What's different about how it runs to be able to do that?
Well, basically what most of the manufacturers do, they do a couple things. So as it loses capacity, we also lose the ability to maintain the pressure differential between the indoor and the outdoor unit when it's too cold outside, because we can't, as we start absorbing heat, the temperatures or the pressure shift. So what they're doing is they do, the first thing they do is if you were to buy, for those people that understand what like a 3-ton heat pump is, like a standard one would be 36,000 BTUs roughly, is that 3-ton heat pump probably doesn't have a 3-ton compressor in it like the other one would. It has a 4 or 5-ton, but because all of the ones that, I'd say 99%, because there's probably something out there that I don't know about, but all the ones that run low temperature that I know of run variable speed compressors. So what they do is they basically rate it to 100 or 90% and run it at that, and then they ramp it up faster than that because they have speed controls in them. So they just pump more. So they're able to pump the refrigerant to keep the pressure up, where you can't do that with a single speed motor compressor. And they have other technologies in there where they're injecting, when you run a temperature that low, which happens in freezers, refrigeration, the compressor overheats because there's nothing to cool it down. You would think there would be, but there's no refrigeration effect left, is they're actually injecting refrigerant back into the compressor to try to cool the compressor down to make sure you can run that cold. So there's some technology built into them that's different than a base model unit. But in turn, that also means there's more technology.
And they must
In 5 or 10 years, that would be
They must
failed.
be more expensive too.
They're more expensive for sure.
to buy.
They're more expensive to buy. 100% they are. So the other disadvantage that happens for us in the coastal climates, because where I'm sizing all my jobs for, is when we size a 3-ton heat pump, a standard one, it's 3 tons and gives us 3 tons of cooling, close anyways. When we go to the hyperheat ones, or the low temperature heat pumps, sometimes to get the same capacity, we don't need a 3-ton anymore. We can put a 2-ton in and it'll give us more heat at the low temperatures than we need anyways, but what ends up happening is we end up undersizing the cooling. So if it's a cooling problem, we have to be careful of that. Variable speed will counteract it. You just got to buy a more expensive, bigger unit, but that'll be one of the discussions after about oversizing as well. So there's a picture of a horizontal loop, the drilled picture is, I can't see it from here because even all of them are fuzzy to me. And then that's an ocean loop that's not where it's supposed to be. So it should be on the bottom. That was floating after a storm. So common problems. This is where I said. So the common problems with heat pumps, making sure they're properly sized, isn't as critical when you're putting in when installers are putting in variable speed, because it'll just ramp to where it needs to be. You still don't want to put a 5-ton in if you need a 2, because you're paying for way more capacity than you require. But you want to make sure, but you can oversize a little more because it will adjust accordingly. But it will still take more power to run than a smaller one. Airflow is another one that's fairly significant that we want to be careful of, which we'll go over duct sizing, but make sure that you're utilizing the amount of air that's required and not running it in the off one high or too low, usually too low airflow, because you won't get the proper distribution or use the coil efficiently to get the heat out of it, so it affects the efficiency. Refrigerant charge, if it's a split system, which most of the ones are, other than geothermal, I guess, and that package water, air to water, making sure it's charged properly, so the person that's putting it in is installing it and setting it up according to the manufacturer's specifications to get you the efficiency and the longevity that it deserves for how much money it costs to put it in. Duct sealing, which when this chart was made, it's a TECA chart, like out of the textbook. Duct sealing wasn't mandatory. Now it's basically because of energy code has basically pushed everybody to try to make sure everybody's duct sealing everything. But if you add them all up, you can screw up a system by 35% if you did everything as worst case possible, but still had it running. So it could make a huge difference for that customer who lives in a house that has very low efficiency bills, and then the next house right beside them is exactly the same row house with the same system, and because they didn't do a bunch of stuff or didn't have the same person that knew what was going on or didn't set it up properly, they could be losing a lot of efficiency, which just means it's costing them a lot more money to be able to run their house. Okay, so staging of equipment. We have a few options, which some of you may or may not know. Single stage, which is basically old school, turn a furnace on, blower comes on somewhere in there, either on time or on temperature, heats the house, shuts down. Waits for it to get cold again according to thermostat, turns on full blast again, heats the house up, shuts down. Pretty basic. To be honest with you, it doesn't have a lot of problems. There's not a lot to go wrong. Okay, then we came into a situation where we had 2 stages. So now we have a 2-stage gas valve. Some furnaces had 2 stages of blower, some didn't, but basically now it can cycle a little bit better if you don't need to go to full capacity, because it's not, depending on where you're from, it's not always -20. Sometimes it's only -5. You need a furnace big enough to go to -20, but you don't need to be there all the time. So now you can run on that first stage instead for that, the spring and the summer, or spring and the fall. So that makes it a little more comfortable. Most of the time, they're more efficient, but not all of the time. It's truly a comfort thing. There's not always an efficiency savings. So, but it is about being comfortable in the home. So you want to make sure you get those things taken care of. Next thing is variable speed and modulating. So depending on which manufacturer you talk to and what's going on, usually gas appliances, they call them modulating. They'll have a modulating gas valve, and it'll rate, if you need 25% capacity, it'll turn the fan down and turn the burner down, and it'll give you that much to heat your house. If you need 100%, it'll ramp up to where you need it to go. Usually more efficient because the systems they're putting in are making it more efficient. The burners are more efficient, everything's more efficient. It's a lot more expensive furnace. So you have that. Variable speed is usually the terminology we use for heat pumps and air conditioners. So because it's a speed of a motor as opposed to the gas valve opening and closing. And then the next one is a furnace explanation, but it explains it pretty well. So single stage furnace, like I said, waits for it to cold, turns up, overshoots a little bit, comes down, and just goes on and off and on and off. You go into an old house with a big, ugly old 50-year-old oil furnace, it's probably even worse than that for cycling on and off. So we can still buy a single stage furnace. It's not like they're obsolete or whatever else. So we can still get that to run. Then we go to a 2-stage, which means if you need the capacity and they're showing it overnight, you need a little more capacity when it's a little bit colder, but you don't need it during the day. Well, it has the capability of running it, so it'll cycle a little bit more, but it doesn't require it to be. And it doesn't have to run that way. It could run for once peak and then go back to the lower one again once it's maintained as well. So, and then the fully modulating furnace or the heat pump would be the variable speed heat pump would be the same, very close to set point. I've had customers complain that they set it to 21 degrees and it started, even though it's still 21 degrees. Well, but it shouldn't start. Well, it's just anticipating that it's going to drop. It starts. It doesn't go to 22. It just doesn't go down to 20. It just keeps it very close. And some thermostats don't show accuracy to the half degree. Some they only show it to the 1 degree. So, but it's still anticipating it and maintaining the house temperature exactly where you want it. So the other thing you have problems with, which you guys are doing most new houses, but you'll do some renos and stuff as well to approve them, is we have big problems when people go from the single stage, big old, whatever, gas or oil or propane furnace, and then come down and go in even into staying in gas. They come down to the modulating furnace. And what happens is they don't know, if it's installed properly, they don't notice that the furnace is coming on. It just cycles on when it needs to, maintains the temperature at a very low fan level, a very low flame level, and then they complain because they don't know the heat's on. So what happens is their house is set to 21, and they don't get up to look, but they phone and they say it's not running very much and it's cold. Well, because they're used to feeling that blast of hot air every once in a while that they're not getting anymore. So it's just a perspective thing. It's just, there's nothing wrong with the house. They're still maintaining 21 degrees just like they did before, but they're not feeling that blast of heat where it's shooting higher than 21 anymore. It's just maintaining 21, or maybe go to 22 and 20, or some very small window if they had a 2-stage. Okay, so blowers. PSC is the least efficient, the most common for older stuff. I don't know, you guys would know more if you looked, but we don't put a lot of them in anymore. They're very inefficient. It's the one where basically they hear the bang and it starts and then it turns off, and then the bang and it starts and it shuts off. So those are usually in less expensive furnaces. There's still, to my knowledge, I haven't read the new 936 yet, but to see if they're getting phased out. But it'll probably be sooner than later that they won't be allowed to put them in houses anymore for efficiency reasons, because they're running 24 hours a day now, if that's what they're using for their fresh air in their house. The furnace fan runs 24/7, so efficiency will cost them a lot more money, which I have that's the thing in a sec. X13, which is, I guess, the easiest, let's just go to the second one too, is the variable speed blower, which is the one that ramps up to speed and then ramps back down to speed, is set up. The X13 is like a base model of that. So it has the efficiency, but doesn't have the ability to be able to give you the ramp up and down speed and the variable control that you have on the full variable speed. So it has a lot of the technologies and it has a lot of the efficiencies if everything is equal and this ductwork is where it's supposed to be. The difference is, which is the next slide, the three-phase option is just me, because there's a couple manufacturers that are using three-phase motors instead of ECM motors. So, but they're very efficient as well. But if we go to here, the PSC motor running in watts is 40% more than an ECM, a variable speed motor, running on high speed, which is bad enough. The bad one is the circulation mode, which they're all running on 24 hours a day right now, including the summer when even those houses that don't have air conditioning. So the difference is that the person puts the PSC motor and they're basically running 300 and something watts compared to 50. So every motor will be a little bit different. Just to give you a scale. So
what does PSC mean? PSC?
Permanent split.
DSM.
Permanent split capacitor. It means it has a capacitor on it to try to make it a little more efficient. A PSC is basically the minimum you can get on a furnace now today. 40 years ago, you could get one without the capacitor on it, which was even less efficient than the capacitor motor. So, and then before that, then there was the ones that had belts and back and back and back for those guys that work on older houses. So, but the capacitor motor is what was seen as back in the day, the step up to get a little more energy efficient. So, the VSM is variable speed motor. And then the 100 watt light bulb, they're just giving you the comparison, but I don't know.
So variable speed. So that one could run at a lower rate when it just calls for circulation.
Well, if they both run at circulation mode, the problem is running at low speed, you don't actually save that much energy on a capacitor motor.
Right.
That's the problem. Is it still consumes the same amount of energy to turn the motor. With the variable speed motor or the ECM motor, or there's multiple different words we can use, it consumes a lot less energy the slower you go. So that you can keep dropping it down the slower you go. It'll hit a bottom, which is probably what they're showing you there, but it'll save you a lot of money. So if you're running basically if you compare them, a 300 watt motor, 24/7, 365, I don't know, I could probably sit down and do it in math. I can't do it in my head, but it's going to cost you some money over the year. So for those customers that are end up getting these less expensive furnaces, they're probably paying a lot more for that ventilation requirement than they do with the people that are spending a little more money on the furnace. And the builder's the one or the mechanical guy is the one who's saving the money on the furnace, not the end-use homeowner. Okay, so this is the other issue we run into is with a PSC motor, is as the static, so if you run smaller ductwork and it's a little like, if you run smaller duct, the static pressure will go up, which is the restriction to flow in the ductwork. If we design our systems to be at 0.2, or for supply and 0.4 if we're running ductwork on both sides, which we usually do. So when we size our furnace and we start adding these stuff up, we look at it and go, the top furnace does 880. Well, if they screwed up and they ran ductwork that was a third too small, and all of a sudden we start going up, now they're getting 200 CFM less than what they're supposed to. This is where we're looking at the efficiency problems like in the other slide, where you're just losing money because you're just pushing more wattage into it and doing everything else like that. The X13 motor is the same, except it would consume the same amount of energy no matter where the static is. It just doesn't change speed. It's a constant torque motor. The ECM is set to a CFM, so whatever the static is, it will ramp up and give you the CFM. It will just cost more for the motor, but the rest of the efficiency of the equipment won't be changed. So if it was a heat pump or a gas furnace, none of that those things won't change, because we're able to get the speed counteracts the static. It'll just keep ramping up to a point, but if the ductwork's really that small, that'd be really bad. But you can counteract it. It's been seen as the retrofit, what they call like toolbox thing for a lot of the guys putting retrofit in and going into houses that maybe had bad furnace installs to start with, that they're able to combat them and put in a variable speed blower and fix some of the duct problems, because it will give you the CFM. It might not be super quiet, but it'll give you the CFM. You're not limited by the furnace. So, okay, comfort factors, air quality things, humidity. Some parts of the province are going to worry about it. Some parts aren't. They're not going to worry about putting in, which is just a quick picture, they're not going to worry about putting a humidifier in it or a dehumidification system in if you live in certain parts of the province, but other parts of the province, they're going to have to do it because it'll be too dry in the wintertime, so they'll be putting in, like I said, I don't know where you guys all are from. I've seen some of the things, but I know some of you guys will need humidity, so to add it in the wintertime, whereas on the coast we don't have to worry about it, so, or very rarely. Next thing is temperature we control, which is pretty basic. It's just a thermostat. So there is no magic number. It's whatever the customer wants. So I have customers that keep their houses at 25 degrees 24 hours a day, and I have customers that keep them at 17 degrees 24 hours a day. Whatever the customer wants. We size the house to 21 degrees, which is what Chris would have went over already. So we don't, or I guess I took American pictures because it's all in Fahrenheit. So we don't go through if somebody, I guess, wants their house to be 26 degrees, the heating guy should probably talk to him, and maybe he has to put a bit bigger system in, especially if you guys are in a really cold climate, because it might not be big enough to get the temperature that high when it's really cold outside. If he wants it lower, it'll be fine. It'll just be a little bit oversized. Next one is filtration. Nothing super fancy. There's a bunch of pleated filters. The middle one's a HEPA filter, and then the other one is just a thicker 5-inch thick filter. So whatever the customer, it's one of those things that we need to consider when we're talking to the customer and what they want. If you're building a spec house, you don't know who's going to move in the house, well, then you can't do much about it. If they're building a house for somebody specific, then we probably want to find out what they want. Maybe they have asthma, maybe they have pets, or maybe they have this or they have that, and maybe we should be putting a little bit better filter in their system so that they can filter the air a little bit better, as opposed to putting in the one you can see through and has a bunch of little strands of fibers going on it and may stop the leaves that are getting sucked into there or whatever else, but it's not going to stop any dust of any kind. The thing to be careful with the filtration side is if the duct system and the rack and everything else are designed for a certain filter, for you to go to one of the renovation stores and buy a filter and then go, yeah, this is the best one that 3M makes, and then you put it in there's a good chance it's going to restrict the air. So the system may have to be set up again to adapt for that filter. So if it's something that's happening for the builders that are in the room, just make sure the heating guy comes back and make sure the temperature rise in the furnace is okay, or the air conditioning or the heat pump is okay. And you can usually adjust it. It's not, if it's a brand new install, there's a good chance you can make some adjustments to it and combat for it, but you have to make sure that you're accounting for it. If it has an ECM blower in it, or a variable speed blower, you won't have to worry about it. It will combat it, but it may get noisy. So just make sure that if you need the filtration, that you're planning it in the system installed to begin with. Okay, next one is purification. Most common one is UV. So there's a duct-mounted one, and then the one on the other one is an object. So you put that on the coil to make sure that you're not growing anything in the drain pan of the coil or around the coil on the fins of the coil and stuff like that. There's a few other ones, some ozone generators and some other things like that you can add. Whoever wants to put it in, that's whatever they want to do. But there's a few options out there to try to purify the air, to try to kill the germs and the molds and the spores and stuff like that in the air. The thing to remember is none of these filter the air. You still have to have a filter. So they're not going to catch any dust. All they do is kill the organisms in the or at least in this case, or neutralize it so they can't reproduce. So they make them sterile so they're still alive for whatever the lifespan is, but most of those spores don't have lifespans that long. They're not going to live in your house for 6 months or anything like that. So this is where I was saying we got to make sure we talk to the customer as much as possible, find out what they want. Because if they decide that you guys go, yeah, you guys quote the job and you go in and you're doing this and doing that and you put a gas furnace in and you go, oh no, we really wanted in-floor heat. Well, maybe that should have been a discussion before they started putting the floor in and before they put the structure in and before they did everything else. So make sure you know what they want and where they want drops or where they don't want drops and everything else like that. It's a good idea to have the mechanical talk to the builder, at least at the beginning of the process, to make sure you can see the plans before it starts so you can see if maybe he'll notice if there's mistakes that will affect what he has to do. Not mistakes, I guess I shouldn't say. Affect where he has to put ductwork in this case, because that's what this clause is. So try to be a little bit conscious of that. Sizing the equipment, do a heat loss like you guys just learned with F280, which is the recognized heat loss program now. There's guys that do other ones. At least they'll be doing something. It's better than nothing, but they should be trying to use F280 as much as possible because it's the most accurate one available right now. There is others besides TECAs for those guys that want to know. There's others. It's this CSA process that you're supposed to follow. So size the equipment right. So things to remember. There's just a basic kind of spec sheet for a furnace. So if we go to the smallest one, it's 60,000 BTUs is what an input is. If it's only 97%, then you're losing 3%. It's not really going to throw you off a whole lot. Not a big problem, right? But if you're putting in 90%, all of a sudden you're losing, or 91 or whatever minimum is. I can't remember what the minimum is now. We don't put a lot of them in. So you're going to lose a little bit more. So just pay attention. So if you're sizing the house, if it's 60,000 BTU heat loss or 61, then that 60,000 BTU furnace isn't big enough. It won't meet the heat loss requirement when it gets to design temperature wherever you live or wherever the house is being built. So make sure you pay attention. That's the highest efficient that most people have. That's just one I picked up offline. So if we go to, this is the question about how big and supplemental and everything else. We go through. So what this is as a heat pump runs outside of the low temperature ones, it will lose efficiency. Lose capacity as it gets colder. So if the heat output in this case is 27, it'll be at 47. Manufacturers size their equipment at 47 degrees Fahrenheit. It's an ASHRAE standard measured time, so we'll just say that it's 25. So what'll happen is as it gets cold, it's going to lose capacity. The other magic number for ASHRAE is 17 degrees Fahrenheit. So you'll have those two numbers for sure. It may not be a perfect linear equation, but those are the two numbers you will always get, is 17 and 47 from every manufacturer for a heat pump. So some will give you more, but not very many. So they'll have those two, so figure out where it is. So what you do is just on a plot a graph, do those 2 points. We consider no heat loss at 65 degrees, or TECA does. They assume you're going to have enough internal gains to heat your house to 72 or to 21. Anything above 65, your refrigerator running, people, electronics in general, sun, whatever, those kind of things. So from there, as it gets colder, it'll go down. So if this house was in a minus 15 environment, Fahrenheit, then it's going to go down and it'll be 27 degrees. So we need to size the backup heater for this situation. If it's gas, would have to be 27,000 BTUs because the heat pump and the gas cannot run at the same time. So if you're using a coil, like a hot water coil or electric coil in the system instead, then you can just supplement the difference between the two and not worry about the bottom part. In this case, it's a pretty extreme difference, but sometimes it's a lot closer. So you would only have to go from the 3,000 to the 20,000, so you could put a little less in. Are you going to do that? You could, but you don't. I'm just telling you, you don't have to fill the whole thing. Because there may be situations like the next slide. Oops. I'll just go to this one to show you. the next slide, this is the one I was talking about that has the capacity, right? So basically it's at the 8 degrees, which is 47. It doesn't lose any capacity till minus 15. Then it starts to lose capacity and goes down to 80% at minus 25. But it's still more efficient than electric heat if that's your choice. If you have gas supplemental heat, you can do a different math balance calculation of where the electricity output of the heat pump compared to what you can get for gas would be. And there's the standard heat pump losing capacity basically, but you see it's not technically a linear line, it's a little bit curved, but it's close enough to be there. So you have to deal with that. So if we go and use the balance point here, and there's just some random numbers. So this heat pump here is a standard heat pump. Single speed, probably most common, 15.5, 16 SEER, which is Energy Star minimums, everything else like that. So if we look at just the top one, it doesn't matter. So the top one is a 4-ton heat pump with a 4-ton matched indoor unit. So our capacity at 47 is 45,500. So it's a little bit less than 48. That's why you don't really have to go by that too much. But when we go to 17, it drops to 29,600. So we've lost 15,000, 16,000 BTUs. It's a lot. If somebody was, it's a 4-ton heat pump, I have 48,000 BTUs, I have a 46,000 BTU heat loss, I'm good. Sure, as long as it never gets colder than 47 degrees, you're good. So we want to make sure that if we're sizing the heat pump or making sure when we have to add capacity, that we need to add capacity from 29,000 back up to the 40,000, 46,000 that the heat loss of the building was. So you're going to add a little bit in there. And then what you'll notice is COP, which is coefficient of performance, is for every dollar you put in of electricity, you're going to get $2.50 of heat at 17 degrees, which is still 2.5 times more efficient than electricity. So it's still better to run the heat pump even at 17 degrees than it is to run electricity if that's your backup or your supplemental source. If you have gas and you're running high efficient gas, there's a good chance that you're already switching over before that point to go to a high efficient gas furnace, because it'll be more cost effective for the customer. Unless, which is where you have to talk to the customer, and I have customers that want to run the non-fossil fuel option as much as they can. They don't want to burn anything other than when they really need to, like when it gets cold enough the heat pump can't keep up. They're doing it for personal reasons, not for cost reasons. So if you look at that, but if you look at that one doesn't lose capacity. So for my climate, I don't have to ever worry about it. As long as that heat pump will meet the heat loss, I don't have to worry about it. So anybody minus 15 and above, warmer, could get away with putting that heat pump in without any supplemental heat and not have any miseffects as far as maintaining that space temperature with the heat loss. We don't count, which I don't know if Chris went over, we don't count the sun, right? And we don't count appliances for winter or people, right? So these things are going to be there for a chunk of the time, especially for those people that are in a little more of the sunny and not the rainy part of the province. They're going to get some sun in the wintertime, which is going to give the heat to the house a bit. So, but we don't count that when we do it, because we don't know if it's going to be there. Okay, so grills. It's just a quick whatever. There's lots of different kinds. I'm not going to go over sizing grills because there's so many parameters that you have to follow. Just make sure, most of you are putting in 4x10 plastic or metal grills on the floor. Great. It'll easily handle the amount of air that comes out of a vent with a 4 or 5 or a 6-inch run going to it, no problem with any serious amount of restriction. Return airs, you'll find that if people sometimes put something with a little more opening in it, if they're complaining about it whistling, the whistle will go away. Because if they put one with a very tight opening, it'll whistle. Just like if you pull a balloon and there's air in it. It's the same kind of idea. It's sucking through that hole, it'll whistle. If the spaces are a little bit bigger, the whistling will stop. The restriction will be less, which is better as well. So that's basically kind of make sure that the return airs are as free as flowing as possible, so you have less restriction, less work on the motor, less requirement for the fan to ramp up and give you guys more CFM that you didn't really need to get. So Sizing. I'm just going to go skip that one. Okay, so duct sizing now. If we go through the basics of duct sizing. Okay, so a properly installed furnace doesn't require these things by code, but it will make your static pressure less if you have less restriction to flow. So we want to try to have it easy for the fan to leave and get the air out, as opposed to being a chunk of duct attached to the top. We want it to be able to curve out a little bit to be able to get the air out easier. So usually the takeoffs are bigger where they're attached to the plenums, and then go to whatever size duct requirement it is. Doesn't matter what size it is. The return air, when you have to turn corners, try to have them rounded inside and outside to easier flow. Filter against the cabinet on the outside. That's pretty standard. Nothing that weird. There'll be some spacing requirements by the manufacturer, but you guys can follow those as required. Return air drop. Most common problem I go to when I look at jobs is the return air drop is too small. The tapered plenum is a great idea, and it will help counteract a small plenum that has to be jammed, because it'll make it easier for the air to come down. But what ends up happening is they have, on the supply side, they run two 20 by 8 ducts running each way. Not uncommon in a few thousand square foot house. The problem is the drop coming down is 20 by 8. Well, it has to suck the same amount of air it blows. So you have to make sure that it's sized according to that. And if anything, the supply air would be smaller because it's pressurized. The return air is a negative, right? So it's trying to draw through it. It's sucking, which is a little bit harder for the fan. So that's the most common. The return air duct across the ceiling half the time is exactly the same size as the supply air. They just run the same ductwork right beside it, or even sometimes bigger, but for some reason the drop is always smaller. So that would be one of the probably most common things to notice. But mostly, if you can get away with a lot more things if you build everything a little bit better, instead of just using spare cut takeoffs and square cut corners and everything else like that. You can lower the static to be able to do it. 2 ways to count duct, or like to size the duct, is equivalent length of duct, which is a ductilator. I had one and I can't find it in my bag, and I only had one. But basically, it's a math to equivalent length of 100 feet of pipe. Will tell you how much air will go through that pipe at a certain static pressure. So the difference is we don't use that because it's not as accurate, or it's not as quick and easy to use, and it doesn't take into account a few other things. But it's an easy, quick check of a job. We count fittings at TECA. That's what we teach in the duct design class. So it sure should be there. There we go. So basically what we do is we count fittings for how much air. The first one off the duct, if you come off the furnace, if we go to the one that says 2 and 3, where it says 3 fittings, that one will get more air than the one that has to zigzag a whole bunch and get all the way up here to this top floor. So we have to make sure that we design the system according to the fact that that will be harder to get air to. So it means we can't undersize the duct from the furnace to that point, otherwise there won't be any air left by the time it gets there. Even with an ECM blower, it won't be able to counteract bad duct, like if it's that bad. So we want to make sure that we size all that back. If it's an up and down house, like basement, duct across the ceiling, another floor on top, everything will be short runs. It'll go up one floor or down, up or down across the whole thing. Pretty simple and pretty easy. It's when you start getting into multi-story houses where you got to start really paying attention to what size the ductwork is. Because even if that first one had the same amount of air as this last one, the last one it's going to be a bigger duct to make it as easy as possible for the duct to get there. And I'll show you in a sec the difference in the thing. So the other big one is that we try to teach as much as possible is both of the third floor ones on that run, or the second floor ones on that run, are using what's called stack duct. It's the oval duct that fits inside the wall. The oval duct isn't actually the problem. It's the fittings that convert the round to the oval duct that are the problem, because they're not very fluid in their flow, like the 90s you can spin. So what happens is we count them as a full fitting, but normal 90s are only a half a fitting. So if the builders are going to group can get their guys to run round duct the whole way, even if it ovals a bit in the wall to fit it in, and round duct, especially the 90s, they'll have a lot more air coming out of that vent with a lot less problems. Can you use stacked duct? Yes, there's nothing against code. You just got to make sure you size it properly to be able to get it there. It's also costs more money anyway, so usually it's cheaper. Supply tables that we use. So we have two supply tables that we use. We have a 0.2 supply table static, and we have a 0.3 static pressure. So what it means is on the 0.2, we're planning on having less pressure in the duct compared to the 0.3. Oops. They do it, yeah. So 0.2 is what we use for a heat pump, because a heat pump requires easier air movement to go across the coil, because it's a little more critical to make sure that we're not going to overheat the coil. Furnaces have a fairly wide range of temperature according to the manufacturer spec. Sometimes they're huge, like 60 and 80 degrees. Usually they're about 30 or 40. A heat pump doesn't have that much. It's a lot tighter tolerance for heat across the coil. So what happens is we want to run a little bit bigger duct for a heat pump than we would if it was just a gas furnace. So if we look at this here and we just look at the first one over there, it says that 8x6 duct will handle 160 to 180 CFM, which is great if it's an up and down house. If it starts getting to a 3-story house, we want to come over here, and if we were in the same, we're coming down to this range, which means we're running a bit bigger duct, right? It's not astronomically bigger, but a bit bigger duct to make it easier, because the number of fittings is now a 7 fitting, which is what the diagram there showed us on the top ones, compared to the easy runs that will be less. So if it's an easy duct job, the duct's a little bit smaller because it'll flow easy. It doesn't have to work any, or it doesn't have to get any distance. So we don't have to worry about it as much. So, and then if we're somewhere in between, then there's an in-between number, but if it's like a 2nd story, that's easy to get to. Yeah.
If you're adding a heat pump as a retrofit, adding a heat pump to an existing furnace,
Yep.
what kind of factors will you run into then? If you're running to the same size of duct with the heat pump?
You'll have to speed the fan up, so it'll be a little noisier. It runs more air, so it's like to get the same amount of heat out of it, it runs more air.
So if you got a 3-speed furnace,
And it was on medium before, there's a good chance you're running it on high, if the fan can handle it. The other thing to be careful is some furnaces can't handle having AC coil on them. Not too many gas furnaces, but there's a few other furnaces floating around that they don't have the horsepower to be able to push through the resistance of the air through the coil. So it happens. It's not common, but it happens. So, but yes, can you do it? For sure you can do it. It's not going to fail miserably, but it's one of those things that you'd have to check. Measure the ductwork, check the calculations and see what you can and can't do, and it may say that you don't have enough. It's some job retrofit-wise, the house may like to have, they want to put a heat pump on and they want to have, they size it to be a 3-ton heat pump, and then figure out the fact that it can't handle the ductwork can't handle a 3, they can only put a 2.5-ton heat pump in, which means the gas will run a little bit more because it'll be a little bit smaller, and hopefully it's big enough for the air conditioning side.
Do you see that problem with the high velocity? They try to put it on high velocity.
High velocity has some issues. The coils in high velocity system are sized differently. There's more square footage of coil compared to a standard A coil above a furnace. There's more square inches of piping and everything else like that to try to get rid of the heat because it's going by faster. So it's the CFM in a high velocity system isn't that much different. It's just the outlet is smaller, so that the pressure is higher. Well, they build up, so like a standard, whatever, we'll say an air handler, we'll get rid of the gas part of it altogether. A standard air handler with a heat pump needs 1200 CFM for a standard, like a normal everyday one, ductwork size perfectly. If you wanted to put it into a high velocity, there's a chance that it's only 1100 CFM. So the return air is probably close to the same size. The supplier just shrinks down to an 8 or a 10 incher, depending on the manufacturer. And then you run the thing. The reason why you have to run the flex lines is to get rid of the noise at the end. If you don't run the flex lines long enough or proper, or size it proper, like follow whatever manufacturer you're using, if you don't follow those directions properly, you'll have a noisy system, which is what some people complain about for high velocity. But if you size it properly and do all those parameters. When they tell you that there's a minimum of 15 and a maximum of 30, don't run 15. It'll be noisier than if you ran 20 or 25 or 30 even, like for the number of vents. You need the air to go somewhere. It's going to give you the air because it's a variable speed blower for sure. It'll give you the air. You just got to get rid of it. You have to disperse it. So if you don't disperse it properly, then you're going to have noise. Is it going to heat the house? 100% it'll heat the house, but you could make a standard duct system noisy by making it a little bit too small too, and not having enough vents. Return airs are basically the same. The farther away it is, then you want to make sure that you size it accordingly. If there's only one return air, it'll be a smaller return than if there's 3 return airs on that duct. So the CFM and how far away it, like how many times it turns, basically. So you want to make sure you counter that up. So if we looked at this one was 60 and 88 was an 8-inch, and if I go to this one, 160, 180 is a 7-inch on a furnace. So it's one size smaller, basically, if you had a gas furnace and you weren't using a heat pump. So, like, there's a lot of charts. Like, I'm not that far off of where I figured. I'm a little bit faster. I talk fast. I apologize. But there's nothing. There's basically the longer the run, or the more complicated the run, you're going to be running a bigger piece of duct. The more CFM, you're going to be running a bigger piece of duct. It's just one of those things. You can't not get it. If you walk into a 5,000 square foot house and you look at the run going across the ceiling and it's not a high velocity system and it's not this big, it's too small. Like, you got to heat the whole house. It's not, like, you have to kind of go, like, this is the kind of stuff that they're supposed to know. This is where the ductilator, which for those guys that are inspectors and want to get a ductilator, just go to one of the HVAC wholesalers and ask them for one. They'll give you one for free. It'll have their manufacturer logo in the corner, but it doesn't matter. Then you can go to the duct and go, it's this size by this size. Look at it, it's 0.2. Look at 0.2 static, and it's supposed to be 600 CFM at whatever size it was, and you know that that's supposed to be way more than that. Well, then you know it's too small. It's pretty easy to use. It's not too complicated, and there's a good chance the heating sales guy will show you how it works anyway. So supply branch runs. So this is the small runs, like the round runs that come off the main lines. So the difference is we have the furnace side and then the heat pump side. So it's basically just over 10% difference in some cases as it goes up, like 35 to 30, 65 to 60, and it goes down by about 10% or so. So just make sure it's big enough. This doesn't mean the answer is to walk into a house, run all the duct and run 6-inch everywhere because you don't want to be too small. It doesn't work that way. You still need to get the right amount of air because you need to keep the static up a little bit to make sure that it gets everywhere you want it to be. All the early 6-inch ones will get a lot more air than they require, and the end ones, if they needed to be 6-inch, won't be getting 6 inches worth of air. You need to size it properly. There's a reason why we can buy multiple sizes of duct. It's so you can size that little powder room. Doesn't need a 6-inch vent. A 4-inch is more than enough, and it's probably even too big. But that's basically the common smallest duct we can get. So I don't know. There's 7-inch on the chart. I've never put 7-inch in a house. So personally, so most guys are running 5, 6, 4, 5, or 6. So, but some guys in their head think that, oh, I was going to run 5. I want to make sure. We'll just put a bigger one in. It's not a plumbing drain line where if you put a bigger one in, it'll just drain and it's okay. It's not that. It doesn't work that way.
And they have this rob all the air.
It'll steal the air, and then you can start shutting on dampers and try to counteract it a little bit and try to fix it. But the homeowner's going to do that anyways because they're going to. The husband or the wife that has an office at this side and then they have another room at the other side, they're going to want less air here, and they're already going to be tweaking it to their personal preference anyways. Don't make them tweak it to the preference of the furnace that has to be now set up differently. Try to make sure that you're getting the right amount of air, which if you do the heat loss according to the way Chris taught you guys, you'll know how to size it per room and know how big a duct, after you take this class, how big a duct you need to get to each room. No different with the hydronics that you guys will learn later.
It's just a path of least resistance, right?
Yes. It'll take the path of least resistance. And the hydronics is exactly the same. We run into lots of houses where the hydronic side, where the plumber's decided that he knows what he's doing and he lays the floor out, and I ask him, okay, so where's the design? And he goes, I've been doing this for 50 years, I'm good. And I go, so how much heat do you get in the room? Oh, it'll be good. How much heat do you get? It'll be good. Well, that's great until you have the big wall of windows that now is losing more than the floor can actually push into that room. And the floors are cemented now in the houses, they're drywalled, and you can't fix it. So It's no different than hydronics. It's exactly the same. If this room requires 55 CFM at 100 and whatever degrees it is, that's what it requires to heat the house. It's no different than the hydronic side. It needs this many gallons a minute at this temperature to heat that room properly. If you don't do that, it'll either overheat or it won't heat enough. You need to get close in the same range so it can shut down. Hydronics, a lot of guys can get by without it because they'll put a thermostat in every room and fix the problem by just shutting it off, and it just cycle lots. Forced air with one thermostat in the middle of your house, you're not fixing that problem. You have to start playing with ductwork and you have to start rebalancing everything. So you don't want to be doing that. Okay, manufacturer's instructions. I don't know. I can guarantee you guys go to a house that's fully roughed in, fully done, everything else like that, and the instructions are just sealed in the bag in the furnace, if not sitting, if they're even there at all. So manufacturers are supposed to stay with the furnace. I know some heating guys don't like to leave the instructions with the furnace so the homeowner can play with it. They're supposed to stay with the furnace. If the homeowner has a book, that's fine. They can put it in the book, but they should be on site somewhere. Is my rule anyways. But I have a picture just at the top of whatever air conditioner. It doesn't matter what it is, but the instructions for everything should be on site so that the next person can look at them, or the homeowner can look at them, or somebody can look at them. You guys can look at them.
With gas appliances, you have to have the instructions with the appliance.
With the appliance,
at all times.
Yeah. Yeah, that doesn't happen.
Yeah.
I've been doing this 26 years. It doesn't happen.
No, we do our inspections. There's nothing there, we reject them.
Yeah.
Get them.
Yeah.
Yeah.
So, well, is everybody in this room building officials, or is there some builders in the class? Is there any builders in the class? No? It's all good. Well, I don't know. Yeah, because I don't think only Vancouver. You guys don't inspect gas. Safety Authority does it for everybody, or does some of the municipalities do it that are
We do
good?
gas with Burnaby.
Do you?
Burnaby,
Burnaby, that's right.
Burnaby and North Van.
Yeah. New West, I think.
And Surrey.
Surrey does, yeah.
Two gas.
Yeah. So do that. Next thing, which isn't required by any code required, but a lot of manufacturers are pushing this to maintain warranty, is they want to start up a commissioning sheet filled out. This is one out of the TECA book. Most manufacturers have one in the back of the installation manual. And if they don't, you can ask them for one and they will give you one. So, and some companies, like we have our own, because I want different information sometimes, but we have our own that we use. But just to make sure everything is okay, this is an old sheet, as you can see. It's saying adjust pilot flame. I just copied it out of the book. But is to make sure that you know what's going on. Then you have a baseline for when the customer complains 6 months later. You have a baseline of what it was doing before they even moved in the house and played with anything. Because if you go back there 6 months later or a year later and it's working exactly the same as the parameters you already tech and you know those are to spec, then you can hopefully adjust whatever they want you to adjust, but maybe you can't. But you wouldn't know. If you didn't check it, you don't know what's going on. So get as much information up front as possible to make sure that you know that it's running properly. Because I know for the retrofit guys, they have to fill them out now to get grants. So Fortis wants commissioning sheets for every gas appliance put in for a grant. Yeah, 100%. So it's not a bad thing, and to be honest with you, they should be checking all those things anyway, so having a piece of paper in front of you and writing it down or whatever isn't that complicated. Just take the information, save it for future reference. Then when, like I said, when somebody complains later or whatever's going on, or when you're going and you go back there every year for maintenance, you can check it every single time for maintenance, and it comes back every single time, and then the next year it comes out weird. Well, that doesn't make sense. The last 4 years it's been exactly the same, and the customer's not even complaining. Well, then you can figure out that something probably changed and talk to them. Maybe they shut half the house down. It was freezing cold up here or whatever. We closed all these vents, and now everything's all skewed because they shut half the air down. Or maybe there's something physically wrong with the filter didn't get changed often enough or something else. Yeah.
How about this a retrofit secondary suite at lower level? Rather than heat pull up and down with the same furnace ductwork and put in the dampers and
They cap it off.
Something like that, because the clock goes off.
Yes.
You kind of warn them, don't do this without advice.
Yeah.
But what's the results of locking those up as well?
It depends on the furnace and how close to. So if you have a furnace and it's allowed to be, we'll say 152 or 150 degrees Fahrenheit, sorry, trade thing. We all talk in standard measure, not in metric. It's supposed to be at 150 degrees Fahrenheit, and they're running it at 145 with the basement running. I can guarantee it won't be 100. It'll be over what the manufacturer wants it to be with the basement vents, without any other adjustments made of any kind. Just somebody capping all the ducts. It will go over the amount. If they're allowed to have between 120 and 150, and they're at 125 before, there's a chance that it's at 145 now, and they're perfectly fine. And it's all good, but it has to be checked out and set up again. If they're blocking one vent, it's probably fine. But if they're blocking a floor worth of vents off, it should be checked by a gas contractor or a heat pump guy if it's a heat pump, like a refrigeration guy, to make sure that it is going to run within parameters and not overheat. Because I've been to them where they were overheating and running on the high limit, right? So the customer's house is hot, but the thing keeps cycling on high limit. That's on old furnaces when they used to have auto reset ones. Most new furnaces, high limits are manual reset, which means somebody has to go do it. Yeah. So, but the other option always is if the furnace is old, when they do the renos, put a smaller furnace in. The ductwork might be a little bit too big, but at least it would be sized and the heat rise would be proper for the space that it's doing. But yes, they don't usually want to spend the money on especially if it's already a new furnace. So, but yes, it's not. Technically, as far as gas code, they should be resetting the thing up if they're adjusting that much, in my understanding anyways. That's what they should be doing. Because it's not running the way that it should according to the installation instructions. So codes, we got gas code, electrical code, building code, and then local bylaws. Everybody's local bylaws are a little bit different. Okay, I don't know, it's a big enough. Okay. I didn't have a big screen to test this on. I was trying to figure it out on my screen. It was not too small. Okay, so this is me pulling out specific things out of different places in the code that are supposed to be followed. Okay, so part 9 is ventilation, part 6 duct, that's fine. Unconditioned space must be insulated to the wall value, which you guys would all know because I'm sure you guys are catching people on that all the time since it changed in 2012 or 14. All returns and exhaust openings shall have grill if it's below 2 meters. So what it means is they can have a hole if they want. If it's on the ceiling, they don't have to put a grill on it by code. Would I put a grill on it? Of course I would, because some kid's balloon's going to get sucked in that thing for sure if you don't put something on there. Fresh air vents will be installed where there's no contaminants. Don't stick it beside where you warm your car up every day. And hopefully the installation guys are realizing that the driveway's right there and maybe we shouldn't put it right where the guy's going to park his truck at night or whatever and then warm it up. All duct joints are supposed to be sealed. Warm air supply in every room adjacent to unheated space. That includes walk-in closets, bathrooms. So if they're heating a bathroom, we haven't been doing it because they're heating the floor. It's still heated, but it should be heated space. It doesn't, this isn't exact wording out of the code either. So one vent for every unfinished area, 40 square meters. A return air should be designed to handle the entire CFM, which I discussed with the drop. Make sure that if you're pushing 1,000 CFM, that you can get 1,000 CFM back. Vertical return air shall not serve more than one floor. That's a fire code issue, so don't use the same wall cavity to go up to the next floor with the grill on the wall. Non-combustible underfloor grills, that's probably one of the more common ones that gets missed. It's supposed to be a piece of metal under, if you cut a hole in the floor, it's supposed to be a piece of metal under that floor, so if a spark drops through, which I'm assuming is what it's for, then it sits the metal and it doesn't start the house on fire. So they're supposed to have a piece of metal in the wall. It's not, it has to, whatever, zigzag around. It's the ones where, and a lot of new houses don't get floor grills. This is a retrofit problem too, but when they do, they should have a piece of metal underneath them. Old ones used to be all metal. They didn't do anything else, but that got expensive.
Put a fire damper
For the floor.
When they go through the floor,
yeah.
Put a fire damper. The heat hits it, it blocks off the entire time.
Oh, there you go. Yeah. So you can always do more than code. At least one return air provided per floor. I don't know. That's it. That's between the installer and the inspector. Sometimes it's impossible to get one up to some of the open plan houses, so you got to figure it out somehow to try to figure out a way to get that as best as you can. But you should have one per floor. Provisions are made for return air in all rooms. Undercut doors is the most common. I've ducted houses where the return air in every single room. It's what the customer wants and what they're willing to pay for, I guess, at the end of the day. So I don't need to undercut the doors if I can put return air in that room, basically. But you need to have some way for air to move. So And then everything will be fitted with dampers or adjustable diffusers. Basically, everybody nowadays, old school, you have the little tab on the ductwork down in the unfinished basement. Most guys just use the one that's on the duct now, or on the grill, so which is fine. If you design the house properly from the beginning, all the vents will be open, and it won't matter. So, to just go by that. So, okay, next. These are common, different ones. Location outdoors compared to lot line, the neighbor of the house, the neighbor's house. Every municipality is different for what the rule is for location of an outdoor unit. So, you guys are inspectors, not installers. So I was told that there was going to be installer, like builders too, but whatever. It's all good. It's there anyways. So some of you guys would have rules. Some of you guys might not have any rules for that stuff. You can put it wherever you want. But some do. Some are, like where I am, it's 15 feet from the lot line. It's not a noise level, it's 15 feet from lot line. That's what it has to be. Whereas I have another one which is 45 decibels at night at the lot line. So if the inspector comes and measures it at the lot line and it's more than 45 decibels, you fail and you have to take the heat pump. So, which is the noise level one. Sometimes, and some municipalities are daytime and nighttime are different. The noise level is acceptable, louder during the day than it is during the night. And then there's some, not so much cities, but there's stratas that don't allow outdoor units at all. So it's one of those things you got to be careful of. I had a job, I won't say which community, that has a noise level bylaw in Greater Victoria area that they put a heat pump in, retrofit, and the electrician couldn't show up. He got stuck on an emergency call, didn't come. So the heat pump's there, it's all piped waiting for the guy to come back. 2 days later, comes back, the bylaw guy's there. Because the neighbor complained it was too noisy. Wasn't even electrically hooked up yet. Wasn't even hooked up yet. So. I know this is, well, for some of you guys, you have to deal with the building inspection and other things too. So.
Because you were so noisy installing it.
I guess so. I don't know. The picture of the drilled one was in a community that didn't allow heat pumps. We put a geothermal heat pump in his house instead. And they wanted to know how noisy it was going to be. Well, you put a heat pump in.
No restriction.
No, yeah.
Just put it in.
Yeah. More and more noise is coming up, to be honest with you, on the island. It's a noise level at period that they're worried about at the lot line. They don't care where you put it, as long as it maintains a noise level. So what ends up happening is you get situations, like if I go back, so that one is 20 decibels louder than that one, which is a lot. So we put a lot of that in, but that's just the contractor we are. We don't do spec houses. I do custom houses only. And then retrofit wise, we usually do custom stuff, not.
Yeah, they can be pretty noisy.
Oh yeah, for sure they can be noisy. So, is there any questions that anybody has? Because if I go through here and get all the way to the, because I know I went through pretty quick. I'm a little bit faster than I planned, but not much. I was trying to get as much in as I could. Oops. So, I was told I had an hour and a half, so I was trying to leave some space at the end for questions. And like I said, I'm a little bit faster because I know I talk a little bit quick than I want it to be. Or if you have any other questions about either of the stuff you guys had earlier today, or whatever else, doesn't matter, or any other heating questions or ventilation questions or whatever. For those guys that aren't going to take the classes tomorrow with the same thing. I don't know what you guys are supposed to go through tomorrow. So, but if you guys don't have any questions, I'm done. So I didn't want, like I said, I'm trying to skim it. I didn't want to get into too much depth in one specific thing. So basically all I wanted you guys to do is basically understand that you guys will have the video access to you guys, so you guys can get some of the stuff that was on the screen if you guys wanted it later or whatever. You can always get a hold of Tekka because I think you guys can get most of those duct sizes and stuff. Like I said, I would go to the wholesaler. You can get a ductilator. It's like not that big. It'll fit in your briefcase, no problem. Ventilation code wise, you guys have the code. It's in the code book. It's not really that complicated. And then, like I said, it's just a matter of, as you guys are going to different houses, you'll see different things and whatever.
Yeah, we just see this like it's really not regulated anymore. People, especially on re and re.
Well, people ask. The only thing I have to pull for a permit is a gas permit or an electrical permit. I don't have to pull any other permit for either one, new or re in the municipalities I work in.
You don't have to?
I don't have a heating permit requirement, no.
Yeah, no, there's no heating permit requirement.
No, the only two I have to do is gas and electrical.
Yeah, exactly.
For any install I do.
And that's a problem.
That's a serious problem.
Yeah.
I don't disagree, because I have to fight with all the other guys that try to shortcut stuff.
People taking out 100,000 BTU furnace and you're putting in a 40 or 60, and then there's no documentation, there's nothing. Just do the gas inspection and you just walk away. It's like,
No, it's bad. The bigger problem we have, I think, to be honest with you, is the fact that it's coming down to the homeowners not making the decision based on what the long-term cost is. The builder's talking them into going, this one's cheaper to put this in instead.
yeah.
And then what happens? It comes down and bites them in the butt a year later, because a lot of the jobs that I personally do, I'm talking to the homeowner at the beginning with the builder. So we're having a discussion through the whole process. That doesn't happen often enough. So
It's not so bad on new construction. It's more the retrofits that people are pulling these towns.
yeah.
And
Nope.
the homeowners are trying to get the cheapest thing they can get there. They just want heat, right?
Well, they want heat, or they want the grant, and they want the cheapest thing that'll get them the $1,000, right? So,
Yeah, that's right.
so
If a homeowner can't decide what kind of heat system to install in their house, is there like a heating system consultant out there that sort of help them make that decision?
what I usually tell people is, if you really want, is pay somebody for their time or whatever, if you can, if you have to. But you basically just have to get different quotes and then decide. But the bigger problem is like, for my company's not a big company. I'm the one that does the sales. So I'm a 27 years in the trade. I know what I'm doing. I can do both aspects. A lot of companies are using commission sales guys that basically memorize the manufacturer's spec book, and they don't know how to answer the questions. So the only answer really is they can talk to one of the modeling guys and get an idea sometimes, but it really depends on what their specialty is. If their specialty is windows and vapor barrier, then it's kind of a little bit harder too.
They have to make their own decision.
They have to make their own decision, and the internet kind of skews them sometimes in the wrong direction too. So you just have to find somebody.
All the fake news?
Yes, I guess so. My answer to everybody when I do the quote is, here's my numbers, here's what I'm giving you, whatever else. If you have any other questions, let me know. And whatever, but I can't do, I said, and they're like, well, and if they don't know who they're going to use, I go, use who you trust, who you think was honest with you and didn't try to sell you something you didn't want. Because I never try to sell anybody anything they don't want. Because I'm not really a sales guy. Well, I don't get paid extra. I got to get the jobs, but I don't get paid extra because I get more jobs. Like, I can only handle so much work. So, yeah.
Does the role of the energy advisor affect your design, your choice of the
Does it?
Yeah.
No. Well, I don't do spec houses, so I'm never putting the low-end stuff in anyways. We do a lot of geothermal and a lot of variable speed product, right? So I'm already up in the level of not putting in a 91% furnace or putting in a 14.5 SEER heat pump or air conditioner. I'm not doing that work. So for us, the energy advisor guys like us anyways, because we're already trying to upsell to that point, up to a higher point anyways.
And that's a good point. That like Ford is giving a rebate for the 97% efficient, 96,
Yes.
97. People are going to that.
They are, yes.
They're not putting in the cheaper product.
No. New houses are getting the cheaper product.
Yeah, new houses are.
So, but like I said, the PSC answer, like I said, the consumption difference is it's going to be a huge issue for a lot of people. Because if somebody had a say in their house and said, no, I want this 97% furnace because I had it in my last house, or I want to have higher efficiency, then they're going to get the ECM blower automatically and all the other stuff like that. Whereas the neighbor and we'll just say they charged them $1,000 to put it in. It's not that much more. So we'll say, because the ductwork is the same, everything else is the same. It's just the furnace itself. So it's $1,000. That other homeowner is probably going to spend that in 3 to 5 years in extra energy costs just because their furnace fan's running all the time. Let alone the gas savings they're getting because they're saving another 5%. It makes a difference.
And it's better comfort too. That variable speed
Variable speed motor, and we don't put a lot of modulating furnaces, and we put a lot of 2 stages in when we put them in, but they always have ECM blowers. Because usually a lot of times we're putting with heat pumps and other stuff. So spending the money on a modulating furnace is a waste when we're putting a heat pump and putting a 2-stage. We're already giving them like 4 stages of heat as it is. So, any other questions? I think we're good then. You guys have a little bit longer break, I guess. What time is it now? Oh, I think I'm not showing the clock. It's after for sure. So, thank you very much, guys.